mais 5. Hoje está mais flexível porque a última não vai ter, então eu deixo só uns minutinhos a mais.
Tá bem. Okay. So, first thanks, Anna, and the committee for inviting me to this important and interesting workshop. Of course, I know that you are more interested in the high temperature regime, quark gluon plasma, these magnetic fields that you are, if I understood, analyzing, that are in fact even larger than the ones I'm going to talk about. But I would like to say that this research, of the effect of strong electric and magnetic fields in superdense matter, or in some sense in the interior of compact stars, is really a very active field, okay? And of course, maybe a little bit speculative if you think about the conditions we have in that stars, but everything now is really changing fast, okay? So I organized my talk. I will give some introduction to compact stars. I don't know how many of you know the field, okay? So, huh?
Since this morning.
You have already a talk this morning?
Yeah, we had one talk.
About who talk about? Yeah. So, okay. So I will see if it's the case or no, okay? And, well, and, but so I was saying, huh? Jimenez, I know. Okay, so let's go. So as you know, where is the pointer? Here. So only for you to know or remember, okay, if you have a star with a mass between 0.5 and 8 solar masses, after you essentially end the fusion of the helium, you get a red giant nebulous, and you get the white dwarf at the center, okay? So the white dwarf is essentially the corpse, okay, or the cadaver, okay, of a star. Normal stars have these masses, okay? So it's the end of our sun, okay? It's a very dense star, as I'm going to show you. But if you have a star, okay, original star, with a mass above 8 up to 25 solar masses, 30 solar masses, okay, the process essentially begins as the same. You have the fusion of the helium, but you can really essentially get the fusion of heavier elements like the carbon, oxygen, sodium, magnesium, up to sulfur, okay? And at the end, you have the iron, this very, okay, dense material. And you know that after the iron, nuclear physics, really, or nature, okay, shows us that after that, you cannot get fusion. Okay, if you want to fusion heavier elements, you need to give energy to the system. So it's not favorable, or it's not exothermic, okay, in some sense. So after that, okay, what happens, you have no more fusion, and so the star first begins shrinking, and so you have really this supernova that is essentially a big bounce, and at the center, you have this neutron star, okay? This neutron star, so is the end of this type of stars, is much denser than the white dwarf, because we have now essentially 10, 12 kilometers of radius. Here we have 7,000, the size of our Earth, okay? So white dwarf has the size of our Earth if it's not so dense, and here you have 10 kilometers. If it's above 25 or 30 to 100, so you cannot really, when you have this bounce, okay, you cannot support still the neutrons that are inside cannot support the collapse, and you have the black hole. Okay? Well, so let me show you, because if I'm not familiar, this is important, okay? So neutron stars or quark stars also, they are not very different in that sense, okay, of the masses and radius. So you have essentially 1 to 2 solar mass, and you have 11 to 13 kilometers. So the average of the density is, is 5, 10 to 14 grams per centimeter cube. Okay, so it's twice the nuclear matter density, because the density inside of the nucleus is 2 times 10 to 14. Okay, because of course in that case it's a very small. So you can see as a big nucleus in that sense, okay? As we are going to see, the matter inside is neutrons, protons, and electrons. Of course, a big difference because it's bounded by gravity and not by the nuclear force, okay? The pressure, okay, is in my unities that are CGS are very, very high, so are 10 to 32 to 10 to 35. I will so if you want to have an idea, 1 mass per Fermi cube that you are used to is 10 to 33, okay? So Dienas per centimeter square, okay? So, so it's 10 or in these units, or in GeV, so you need to multiply by HC, I don't know. And white dwarfs. White dwarfs, you have like 6,000 or more or less, or 7,000, okay, of radius, so it's like 3 orders of magnitude larger, but you can have a limit, as I'm going to show you, but you can have essentially 1 solar mass, so the density really goes down with R cubed, so goes down almost 6 orders or more or less, so no, 9 orders of magnitude, okay? And the pressure also, but it's still a very big pressure, okay? So this star, the density is so high that we don't have more, okay, the nucleus, the atoms, neutral atoms. You have ionized matter, okay? So you have carbon, oxygen, and with a lot of electrons, free electrons around. And here, you break the atoms, and you have protons, neutrons, or maybe quarks, okay? And so this is the scale. This is important. They are quantum stars in the sense that these stars, okay, these stars here, the temperature, okay, is not 0, okay? The temperature of a neutron star is 10 to 8 Kelvin, okay? Our sun has 10 to 4, okay? Or 10 to 3, 5,000, 6,000. But density is much higher than the temperature. So in that case, the temperature has no effect on any of your physics here, if it's, of course, at that order, 10 to 8. Why? Because if you remember, 1 MeV, if I convert as KT, is 10 to 10 kelvins, okay? So our scales is MeV, and the temperatures are 2 orders of magnitude lower, and this also happens with white dwarfs. So only if you have really temperatures like 10 to 7, you can really have effects, okay? But they are not cool. But in that case, so why I say that they are quantum stars? Because by temperature, all the other stars are stable by temperature, okay? Thermal energy or Boltzmann law, or you want, okay? Here, the temperature is not enough to support gravity. If you calculate m over r squared times g, that is surface gravity, it's too high for this pressure, like let's put ideal gas or even with so you cannot support. So this star exists because the electrons are fermions. You have Pauli principle, so you have a pressure that comes from the fact that you cannot occupy more than 1 or 2 states if you have spin up and spin down. It's very, very beautiful, and I always give, when I give these talks, I always say that if someone tells you that quantum mechanics does not make sense, tell him to explain white dwarfs because they exist, okay? And they have no answer. And more than that, the fact that are quantum stars, and these pressure comes from free electrons that are there, okay, surrounding these atoms. This implies a maximum mass for this star that has never been, until now, found any white dwarf with above that mass. So it's really, in fact, this gave the Nobel Prize to Chandrasekhar. Okay, so these are, you know, if you have a Fermi gas, so you have the pressure is proportional to the density, 5/3 non-relativistic, ultra-relativistic 4/3, so the pressure usually in an ultra-relativistic system is smaller than a non-relativistic. If you don't know, that is what happens, and in fact is why maybe it's hard to have quark cores inside of neutron stars, because the pressure usually goes down if you don't, of course, if they are free, okay? And so this is the basic of the thing we do when you solve stars. We just compute the hydrostatic equilibrium. This is Newtonian, so this is the difference of force year to year. So essentially the pressure inside is larger than at the surface, okay? And so this is the force. If you go to general relativity, okay, you have really these three terms, new three terms, if you think about. So these are terms, in fact, that this one and this one, you can think as the pressure, okay, this is the pressure, okay, over the energy density. So if you have a non-relativistic system, the pressure is always much smaller than the energy density. In fact, the pressure is never higher than energy density, okay, because this implies sound velocity equals c, sorry. So this goes out. This is also a pressure over some m over a volume, so it's a density, so it goes down. And if this last term, that is the metric, is the term that comes from general relativity that curved space, okay, if this term is, you can really take it out, you get Newtonian physics, okay? So these are essentially ultra-relativistic terms, okay, and this is the metric. One thing for you to know, if you don't know, okay, is that if you always, sorry, here I have c squared equal 1, okay, but usually if you calculate this quantity, sorry, g 2m over c squared, okay, this gives you one, okay, in Portuguese and now in English, I don't know, 1.5, okay, 1.5, okay, it's not 1,500, okay, maybe, so it's 1.5 kilometers, okay, sorry, without these two here, okay? So this means, of course, because this needs to be dimension of length, because here you have one, have no dimension, no? So with this c squared that is missing there, so this means that if you have, so this term is 3, okay? 2mg is 3 kilometers. If you have 10 kilometers, so this is 0.3. So for a neutron star, okay, with a solar mass, this number is 0.3. If you have two solar mass, that is the most massive neutron star found until now, more or less, so this gives you 0.6, 60%. So instead of dividing by 1, you are dividing by 0.4. So no way to do neutron stars without Einstein theory, okay? For white dwarfs, it's the same if you have a white dwarf with one solar mass, but as you know, the radius, I said, is 5,000 kilometers. So this is 10 minus 3 for us. So no space is deformed around white dwarfs, okay? But I explained that, but okay, let's continue. Okay. So white dwarfs, only very massive white dwarfs, and in fact, this is the work I did with some students, only when these pressures and energy densities are very nearby, that is very, very massive ones, this expression is different from this one. So general relativity is still important for white dwarfs, but only when they are very, very ultra-relativistic or very massive. But this is another story. So what you have is this. So for white dwarfs, you have this 10 to 4 kilometers. After you have this instability, essentially, I will explain after if you want. And after you have this neutron star, okay, with 10 kilometers, this is Landau levels, Landau neutrons, okay, Landau did this game using free neutron gas, okay, and obtained already 0.7 solar masses. So for neutron stars, quantum physics gives you 0.7. To come here is because you have strong repulsion when the protons and neutrons are very close together. This is something from nuclear physics. That you know that when they are separate for 1 Fermi, they are attractive, so you have the nukes. But when the protons and neutrons are very nearby as 0.5 Fermi, you have a hard core in the nuclear force. And this is the strong pressure that gives you these two. And that is the problem nowadays of our nuclear physics. We don't know how strong is this hard core when we increase the density. So our models were not giving more than, at some years ago, like 1.8. Now that we found 2.1, 2.2, so now, of course, people are trying to understand. We need data to understand what happens with the nuclear matter at high density. This will come from Germany, I believe, at least 2 times nuclear matter by far. Okay, so quark stars, okay, and neutron stars. This is a neutron star, quark stars. Quark stars are essentially made of quark matter, so I think Jimenez already explained today. And you have this outer, maybe this outer crust, okay, of that is essentially very heavy nucleus or nuclei with the electrons, so more or less like a white dwarf, okay, and but very small, okay. This is maybe half kilometer, okay, of the star. For the neutron star, you have a crust of at least 1 to 1.5 kilometers. And so we know this physics, okay? Out here, you know that you have these heavy ions, electron gas, because it's very similar to white dwarf, okay? But when you go inside, so here you have already these neutron, protons, electrons, moves free, and inside here maybe superconductivity, hyperons, neutrons, so here no one knows, okay? And maybe quark gluon plasma, okay, or quark, free quarks, okay? So this is essentially, so I think I have here a slide. It's too long, but if you want, I will only go slowly, okay? So quark stars, I think the most important difference, of course, they are made by quarks, and these are made by neutron, protons, and electrons, okay? But maybe the most important is that quark stars, they are bound essentially by the nuclear force. So let's put our equation of state generates a very low pressure, and the density, since you have a vacuum that comes from MIT back model or Nambu's or Nanazino model, so you have a way to get pressure zero with a very high density, okay? And so in that sense, these stars at the surface of a neutron star, you have an energy density that is too high. Since at the center can be 1 order or 2, 1 order of magnitude higher, so the energy density inside of quark star change much less than in a neutron star. A neutron star go from 10 to, I don't know, 35 to 0. Okay? So the energy is almost constant inside of a neutron star, so the mass goes with R cubed. We don't have that with neutron stars. So this is very different. Okay? In neutron stars, you have essentially that the radius decrease, the mass increase. Here, no. The mass increase with the radius because the mass increase with the volume since the energy density is constant. Okay? So these are different things. These electric surface fields that I will talk about, okay, in my talk. So white dwarfs, as I said, are degenerate matter, helium, carbon, or other possible reactions, and they have this degenerate matter, this normal gas of hydrogen usually outside. The more common are carbon ones, okay? But you can have also some heavier like oxygen or neonium, okay, inside, okay? So are different. So you see you have still nuclei, but ionized, okay? The difference of white dwarfs and neutron stars. White dwarfs, we know the equation of state. And it's why I've been working more with white dwarfs in my last 5 years. Because here we know what happens. So it's essentially a Fermi gas with the mass, and the mass comes from the ions, and of course a lattice that you have a crystal, so you can calculate this energy from the lattice, and no more. So you can do that, but in fact, what happens is that if you really calculate the equation of state, and Chandrasekhar did with this essentially ultra-relativistic, so said this is so high that all the Fermi momentas are already much higher than the mass of the electron, okay? Of course, it's an extreme case, and they obtained these 1.44 solar masses. So white dwarfs cannot have a mass higher than this. And in fact, until now, the maximum is 1.38 with some uncertainty. So is really, I think, we understand white dwarfs. Neutron stars, we have a problem because we don't know what happens with the matter inside at high density or the equation of state. Okay, this is even I only say this thing, and relativistic Fermi gas and non-relativistic Fermi gas, because why I show these plots? Because nowadays, many people in neutron stars are trying to fit M over R curves with equations of state that are non-relativistic. But after some density, the Fermi momenta is comparable to the mass of the neutrons. So you need to put relativity. If not, you can't get any mass. Okay? So it's not because you get a very high mass, okay, that is correct. You need to see the physics, and if the Fermi momenta is higher or no than the mass of the particle or the energy, or, you know, that is the case of relativity. So cannot forget relativity when you are trying to do very massive neutron stars, as people are doing many times, because they fit. Well, you see, they could fit here, no? White dwarf with 1.75, but you don't, until now, well, it seems that don't exist. Okay, so.
You mean people don't use TOV equation?
No, they use TOV, but they use an equation of state of the pressure with energy density that is based in a non-relativistic expression for the energy density. It's like P squared over 2m, and they put the effective mass, and they don't use linear, they don't use the linear equation or linear dispersal relation of the energy with the moment, the square root of P squared. That is relativity, okay? Okay, so I would like only to tell you, because I speak a lot, and these are important things, because if you understand this, I think you can get something from my talk today. Oh, so 10 minutes still. Okay, that's good.
I said 5.
5? Okay. So, but one thing I would like to tell you is that this thing of white dwarfs, neutron stars, and also quark gluon plasma, they have scales. They have scales. And if you are out of the scales, neglect. So find your scales. I think you already found, of course. No, but you have scales of temperature, of mu, of magnetic fields, and if they're out of the scale, forget, okay? So here is scale, because this is the pressure of a neutron star, 10 to 32, 10 to 35. The magnetic energy in CGS, because this is what I'm going to use, is B squared over 8 pi. So, and in fact, Gauss square is Dinas per centimeter square. So it's only get this number, okay? Put 10 to 16, square 10 to 32, divide by 8 pi is one scale, so it's 10 to 35. So 10 to 16 implies a pressure of 10 to 31. So no way, zero pressure. Okay, the same thing of course, strong effect, 10 to 18 Gauss, because in that case, 10 to 36 divided by the 1 over 10. So this gives you 10 to 35. So you are here at maximum pressure. So when you have a magnetic field of 10 to 18 Gauss, you are going to change the pressure and the energy density of your star. And so your star are going to have a magnetic mass and a change on the radius. But if it's lower than this, forget, zero. Okay. So it's what I said for the temperature. 10 to 80 is very high temperature, but for the scale of 1 MeV is zero. So zero temperature is a good approximation for neutron stars. For white dwarfs, okay, you can also do for electric fields because this is the energy density of the electric fields, okay, I square over 8 pi, so you can do, of course, this is state volt per centimeter, but you convert, it's essential to orders of magnitude. So if the electric field is not 10 to 18, that give you this pressure, okay, no effect of the charge. Any charge you can put there is zero, neutral, equal to neutral. And of course, strong effect is going like 10 to 20 because you arrive to this pressure. For the white dwarf, since the pressure is smaller because you have a larger rate, so you have a smaller gravity, so it's the same. So white dwarf 10 to 13 Gauss. If your magnetic field inside of a white dwarf is not 10 to 13, no effect of magnetic field in the structure of the white dwarf. Structure means changing equation of state, so changing mass, contribution from the magnetic field to the mass, to the radius, okay? So this is important, and also for the white dwarf. Why this is so important to understand? Because these are very high fields. If you go to the nature, sorry, forget this a little bit here, come here. Maximum, usually, high B pulsar have 10 to 13 Gauss. Okay, so to have an effect of the magnetic field in your neutron star is 10 to 17 Gauss. So it's 4 orders of magnitude higher than the surface of your fields. Magnetars, they talk about 10 to 14, 10 to 15 Gauss. In that case, we are only talking about 2 orders of magnitude higher. Okay? But I should tell you, I believe this is not correct. And the data now are coming. And many of these magnetars don't have these fields. Now again, 10 to 11, one that was a magnetar. So this model of magnetar, we'll see, we'll wait.
Yeah, because now people are saying that inside the magnetar is
Yeah,
bigger than
but now it's hard. If you don't see any field outside, you need to say that you have 5 orders of magnitude of the field inside. Now you need to explain, well, from where it comes, because it's not normal. You don't have these things in our world, changes of order. Yeah, you can have 1 or 2 orders of magnitude. Higher than that, what is this?
But you're expecting new data on this.
Yeah, in fact, now we know that we have a polarimeter in X-rays. This is a new technology now. And they already found one, and they found a very low polarization for the gamma ray, and was expected high polarization because of the high field. Many people don't like the magnetar model because it's the only model in our world where the magnetic field is the response for everything. And the diffusion magnetic field have effects of magnetic field in our world. But the energy, all the energy, we don't know. If you know any system, tell me where is really the energy comes from the magnetic field as the dominant phenomena. Okay, well, and the white dwarfs, and again for white dwarfs, see, 10 to 8, 10 to 9, they found one. This is what is nice of this field, because recently, with these new equipments and even some telescopes and even in this international space station, they have good new let's put cameras very sensitive. And so they found a white dwarf isolated with 30 seconds of period that is almost breaking, because breaks at 2 or 3 seconds of period, with very high fields. So they have found a lot of things. And so, but see, 10 to 9 comparing to 10 to 13 is still very far. So it's still very far. If your maximum surface of a white dwarf is 10 to 9, and you need to think about 10 to 13 Gauss to produce any magnetic effect inside of a neutron star, or in this case of a white dwarf, okay? So let's go. So another thing also, you have this critical field, that is the field, the frequency of the electron, cyclotron frequency, when the energy of cyclone frequency is equal to the mass to the energy of the electron, the rest mass, okay? And so after these fields, maybe nonlinearities will need to be considered in Maxwell theory, so things are more complicated. And of course, for the critical electric field, that is 10 to 16 volts per centimeter, if you come here, neutron stars, okay? Neutron stars if they have these fields, they will create pairs, and so they will destroy the charge. So it's almost impossible. For white dwarfs, at least the electric field maximum to produce effects is below the critical field, so you don't have pair problems. In fact, I have investigated charge effects on white dwarfs, but I will not talk about. Okay, so magnetic white dwarfs, this is something that is going to appear in the book, a chapter I did with some students. So what you have when you have electron gas and the strong B fields, this was already shown. I think the most important thing is that you have a magnetic mass for the electron, and the magnetic mass for the electron depends on B over BC. BC is the critical field. And when this number is small, no quantization. Quantization only appears when this n is almost 1 or 0, so the lowest levels. So this means that B, comparing to this critical field, needs to be higher. So 10 to 13, 10 to 14 if you are electrons, okay? If you are protons, remember, goes with the mass square. So proton mass 2,000 higher than the electrons. So the critical field for protons are, I don't know, 6,000, 6 orders of magnitude higher, okay? But so this is important. So what you do, we calculate this effect of very magnetized matter, okay, inside of a white dwarf. Another thing important that I think you know, but the parallel pressure to the field and the perpendicular pressure to the field have a different sign on the, let's put, book pressure. I understood that in your quark gluon plasma things, you don't consider these things. I hope that you are correct, because if not, everything you are doing has no sense, because this is much higher than the magnetization, much higher. So here, of course, you have a field. The field is there, fossil, or from where it comes. So you cannot have a field without energy. Okay? You cannot have a magnetic field without the energy. Of course, if the energy comes from some place that is not affecting your dynamics, is correct. But it's affecting, you should, I don't know. It's something that, because I always ask you why you don't consider this. But because this is, so what I want to tell you, if this B is 10 to 13 Gauss, this pressure parallel to the field, of course, I'm considering a constant magnetic field in the Z direction, okay? So the pressure in the parallel to the field is smaller than the perpendicular, okay? So it's what I show here, okay? This is parallel, okay, perpendicular pressures, okay? So you can see here more or less where are these here, okay? So parallel, perpendicular, smaller, sorry. I think the sign is changed here. No, it's correct. So it's smaller, And yes, higher, okay. And so this is what happens. You can, so when you have a very magnetic field, you have problems because if you have a large magnetic field, you have more energy, positive energy, so gravity that is negative, so now needs to have also let's go against the positive energy from the magnetic field. So very large magnetic field does not allow very large radius, okay? Why? Because if you go down from the radius, so what you are doing, you are essentially weakening the gravity. And so in that case, the star explodes, okay? So it is, and another interesting thing is that when you have magnetic fields, you always deform the star, okay, if they are very large. So essentially, the radius here is, in this case, smaller than here, okay? Okay, I have finished. And now, to the end, this is a possibility of very magnetic white dwarfs, but these very large fields, okay, they are really have problems with some nuclear reactions. And so this is an interesting paper from nowadays where they have really discussed these magnetic fields of nucleonic and hyperonic stars. But see, you are always talking about 10 to 15, 10 to 16 Gauss, okay, that of course maybe if you have a magnetar with external fields, they can maybe. So what they did is that they essentially showed that hyperons, if they have magnetic field, they can get some magnetic mass, and so you could maybe have two solar masses with hyperons. Here is without hyperons. And I think, okay, I will leave these strong charge electric fields for quark stars for next time. Because this is something, okay, I can talk if someone asks. Okay, that's it. Assim. Here is the group. This is our group at the ITA, where you have some professors from Peru, was a postdoc here, Jaziel, now Espírito Santo, Paraná, ABC, Colômbia, Uniandes, so a visiting professor.
Manuel,
So, yeah.
just one quick question because we want to go get coffee.
Yes.
It's regarding your observation. I think it's a point very well taken. I'm not an expert in your field, but what is the effect, for instance, of we know that there is dark matter. So in general, dark matter will contribute to the gravitational energy of your object, although you don't see it shine. So if you include sort of estimates on the amount of dark matter that an object with such a huge, intense gravitational field can cluster together with the shiny stuff, how do these effects change your estimates on the magnetic or electric energy that you need inside?
Yeah, so that is, I don't know. I don't know. I have a lot of works now with dark matter inside of neutron stars. All them very speculative, okay? All them, if you have a candidate, fermion, let's put, with a very high mass, okay? The pressure goes with 1 over the mass, essentially. So you don't have larger pressure, but you have larger. You can increase the mass. So the problem is to make the balance, okay? Many times, so depends in the model you are using for your dark matter. They generate potentials there. So I don't know. I think the problem you can get, but usually you can get more mass. Usually you get larger radius. That is almost something that you have, okay? Like electric fields also generate larger radius, okay? But, and also more or less mass depending in your model, okay? But it's a field, it's possible, why not? If you have some, so it's possible, but I think we don't know too much about dark matter, but I think it's interesting to solve it. Now, as I said, until when you don't know anything, you can do everything. So they are doing it, okay?
Okay, so we can continue.
Thank you.